You didn't see that.
You want me to put this right here?
Okay, let's finish up this challenge problem, and then we can get in some more stoichiometry before y'all leave today. I think some folks found out last night that the Schoology works pretty well for you to ask me a question, because I get your question and I can answer your question immediately. Okay? As soon as I see it, I try to do that. That is, y'all, that is a huge resource for you. Please use it.
Can I use it this weekend?
Yeah. I might not get back to you as fast, but yes. All right. So, how do we find O? That's the challenging part. We had started this problem yesterday. Shh. Make sure today you're going to need, for whatever time we've got left here, you know you're going to need your periodic table. You're going to need some type of calculator. Shh. If you need one, get it quietly. Shh. What? Yes, and I know that. Y'all that were out with a pass is okay. I got you. All right. So we still need oxygen here. Let me find my stuff. All right. We settled in? Now, what did I just say? What's the reason why we can't do the oxygen just like we did the other things? Because in this reaction, this oxygen right here is part of both of these. Okay? So some of it's going to go here and some of it's going to go there. So we can't find it the same way. So what are we going to have to do is, and this is going to sound crazy, but just trust me, this is one of these thought processes, logical thinking things where you kind of have to go through your process and you have to really know what's going on. Okay? To figure out, okay, well, I've got moles here. If I find, and think about this, because we know about percent composition and we know how a compound is put together. If I find grams of, can I find grams of hydrogen from this information right here? Can I find grams of carbon from this information? And if I know grams of carbon and grams of hydrogen in that molecule, this CXHYOZ, if I know those 2 grams, then I can figure out this one, can I?
You just have to subtract 3 oxygen.
Well, don't think of it that way quite yet, because it's a percent, right, that's going to add up to 100. This percent plus this percent, and then this right here, I should add up to 100%. So I just got to figure out what I'm missing here. All right, so can we convert those 2 to grams first? Yes. And y'all can do that, right? Let's do that. You can do that on your own. And I'll be right here with you. Huh? That one that I gave you that's on the AP exam? Uh-huh.
Do you have another one?
You got it. In your reference sheets. What we might need to do with that, I might send, since there's only 23 of us, let me send some copies on a bright colored piece of paper to the library and get a set laminated. Okay? And then y'all will have it, and I'll keep a set in here, and y'all will have a laminated set. That way it's easy to find. Okay? Will that help? Okay. Because when it's on just a flimsy piece of paper that looks like everything else, it's hard to locate. Plus, you know this thing you're going to be pulling out to use all the time. You're going to take it to lab with you and everything else. You don't want to get it all messed up. Now you're going to get picky. All right, we're just converting for, this is kind of like our warm-up where we've got mole on the bottom, okay? I'm just gonna go right there. Whoops. I just stuck that on the end, do y'all get about like .486 on the second one? Because it's times 1, right?
The mole for carbon is .3638. You messed it up, you try to turn that G to an 8, remember? So when you put it in the picket fence, you want to put it in the mole.
Are you at the top one?
Let me count. You see it? Like the first time we did it, like the mole of carbon, it was 3638.
Oh, thank you. So that's why we can't see anything. That's why I can't figure it out. Like this. I am so sorry. All right. So now what do we get down here? Are we okay still? .363. 3. Okay. And now we get, what do we get here? And can I leave it like that? Grams of carbon. Thank y'all. Can't read my own stuff. Is it close? Do you get something close to this?
366.
Close enough. Okay. All right. Now this is basically multiplied by 1. Okay. Now I've got grams of carbon and grams of hydrogen. And don't I know, look up in the problem, it tells me how many grams of that unknown carbon compound I've got, doesn't it? See? Yeah, let me scooch it back down. And I wrote it right up here, see? It's in the problem. It says I've got 10.68 grams of that. So that's my total, right?
Yeah.
So can't I find how much oxygen if I know all that information? I know the total. I know grams of this, and I can find grams of that because I've got some math skills, right? Okay. So like I could say, well, 10.68 is my total minus I've got 4.368 or so grams of carbon plus 0.486 grams of hydrogen equals. Will that get me where I want to go? Y'all do this little calculation, see what we come up with. It doesn't, it's close to that. It's okay, y'all. Y'all, do not get caught up if our rounding's a little bit different at the end, okay? You're still going to get the same answers. Yeah, y'all have got that on the brain, I think. Statistics. I hope it stays that way. I got like, and nobody panic. You should have something close to this, like 5.826. Okay. All right. Now, I'm out of room. And y'all probably write even bigger than I do. What does this mean to me? I'm just going to write what you would do next, but we're not going to do it. Because now I've got everything that I need to do to find empirical and molecular, right? Because I've got grams of oxygen, grams of hydrogen, and grams of carbon, right? Then you convert to mole, then you divide by the smallest, and those are your subscripts. I had to figure out how many grams of each one I had so that I can convert it to a mole, so that I could divide by the smallest and then do the empirical formula. So I'm just showing you, you can do the empirical molecular stuff even if you don't think you have all of the information that you need. They're not always cut and dry like the problems that I give you. The problem on the test will be cut and dry. It won't be something like this, okay? But you're going to have to think about some things. The last question on the homework, y'all had to think about, actually that was a question from the first test that I gave last year. Okay, that's why I put it on there. Where it gave you so many moles of nitrogen, so many moles of hydrogen, and it yields ammonia. Well, you had to first write the balanced equation, remember in the Brinkelhoff's formula for ammonia, you had to balance it, and then you're just going mole to mole for each reactant, right? So even though it's a basic question, it threw some folks off because you having to go start from the beginning. You have to remember your formulas. You have to remember your Brinkelhoffs. You have to remember to balance it. And then you have to remember, how do you know what the limiting reactant is? So the question was like this long. That's an exaggeration. But there was a lot of thought that had to go into it, okay? All right. Always remember, if you are working with a chemical equation, it has to be balanced, okay? What law says that? Conservation of mass. Never okay to work with an unbalanced reaction. Remember your flow chart and foldables from last year. If that helps you, wonderful. If they don't worry about them. I'm never going to require their use, but if it helps, you can't use it on a test. But if it helps you with homework and thinking through things, then use it. Okay? We're going to always use the balanced reaction coefficients when converting from moles of one piece of a reaction to moles of the other piece of the reaction. Remember, the coefficients in the balanced reaction are how you get from here to here in a reaction. Okay? And we'll do some examples because some of y'all are looking at me like, what is she talking about? You know. It's just hard to think about. What do you have to remember about the volume of a gas? Let's write that in here. At STP, the volume of 1 mole of any gas, 22.4. And at STP, what does STP mean? Standard temperature and pressure. And we're going to get to gas laws here pretty quick. But that's just, it has to be at a constant state. Okay? 1 mole of any gas is 22.4 liters. And that becomes one of the conversion factors we need sometimes when we're dealing with gases at STP. All right, let's do some stoichiometry. And I'm going to see, y'all going to do this for me. Okay? We're going to see what we do. This is summer work stuff. Okay? Summer work was review. This is review. This is all what you can expect on the first test. Of course, there won't be this many questions. You'd never have enough time to finish it. All right. I even gave you the reaction here. But is it balanced? So always, remember, always check that first. If you see coefficients, assume that it's balanced and I balanced it correctly. I would never trick you, okay? But if you don't see any coefficients, check it. Is it possible to not have coefficients and be balanced? Because there's always an understood 1. And then that's possible, okay? But always check. 2 irons and 1, so I already see a problem right there, right? And remember what I told y'all, if you've got 3 on one side, or excuse me, we don't have that here, do we? Never mind. Yeah, but I don't have 2 of oxygen over here and 3 on the other where I can make them both 6. I thought I did, but that's not the case here. This is not a bad fix. I think all I need is a couple of 2s. Is that right? Okay. And those 2s are important. If they're not there and you do your picket fence without your 2s, you're going to mess it up. Okay. All right. This says, how many grams of each reactant are needed to produce 15 grams of iron from the following reaction? So the only product I'm looking at here is 15 grams of iron, right? So I want to know, I know 15 grams. And remember how we did this last year. We always wrote up underneath it what's given in the problem, because that helps you keep everything straight. But I don't know, what I want to know is this and this. So I need a picket fence. I need a picket fence to take me from iron to iron 3 oxide. And I need one to take me from iron to aluminum. And that will answer the question, won't it? It'll tell me how much of this I need and how much of this I need. But I have to do 2 picket fences. Okay? So you always start with what you know, 15 grams of Fe. And how do I get rid of gram? I have to use the molar mass. And I'm going to have gram on the bottom, 1 mole of iron, 55.85 grams.
So you would have to make it 2 because you had coefficient?
No, remember, when you're doing molar mass is always per 1 mole. The only time, look, Y'all remember, because everybody's going to probably, most of y'all need to hear this. When I need these coefficients is when I get to the point where I'm going from this to this. Because I need to know for every 2 moles of iron, I've got 1 mole of this. And for every 2 moles of iron, I've got 2 moles of aluminum. That's where those are going to come into play. Molar mass is always per 1 mole, no matter what. Okay? All right, so that's gone. Now I need to go from moles of iron to moles of iron 3 oxide. Because see, look, I got to get rid of mole of iron. I need mole of iron here. I've got 2 moles of iron in my reaction for every how many moles of iron 3 oxide? 1 mole. But it wants to know how many grams of each, right? Not how many moles. So now I need molar mass again, so I can go from mole to gram. Remember, every time you're going from gram to gram, it's long. Those are your longer picket fences. So, remember, molar mass is always per 1 mole, no matter what. And y'all tell me, I got to trust you now. 159.7.
Man.
All right. And y'all tell me what you get here. Should be like 20-something. I rounded differently. That's why I don't want to write my answer. Y'all get upset. Just tell me what you get. 21.4. And that has 2 sig figs, so I'm just going to say 21 grams of iron 2O3. Now that answered some of my question, didn't it? Because it told me how many grams of one reactant. This wants each. I've taken care of this one. Now I've got to do the same thing, but I'm going to go from grams of iron to grams of aluminum. So y'all do that. See if you can get it set up. It's the same thing. I'm just going from iron to aluminum this time. Hmm? You can just squeeze it in right up underneath. Uh-huh. Because that's still all you really know from the problem. Now, here's what I want to tell you. Until you are experts at this, some of us want to try to skip a step because mathematically you know that 2 over 2's cancel each other out. Don't do it, because you still need to know this. You still need to keep yourself straight with, okay, that's moles of iron. Now I need molar mass, 1 mole of aluminum. If you start getting overconfident with your math skills, which y'all are probably way more competent at math than me, way more. But you don't get overconfident with math skills in chemistry, because you really need to spell everything out until you get expert level, okay? And how many grams of aluminum is in 1 mole? I'm just going to put 26.9 because I'm out of room here. All right, and then we've got to work that out, and I got something like 7.3, something like that. Y'all, is that good? Okay, nobody's going to argue about that. Everybody's okay? So now I know that I need 21 grams of iron 3 oxide and 7.3 grams of aluminum if I want to end up with 15 grams of iron in that reaction. That's what I just figured out. Okay? There's nothing here that y'all haven't done many, many times. I think the problem's going to come in is learning how to interpret what it's asking from you. Okay? And if you'll take it a step at a time and write stuff around it, circle and box it, you know, really talk yourself through it before you even get started. Okay? All right, this is a pretty good test question right here, because this brings in what you should know about the formula for density and some stoichiometry stuff. Yes, sir.
On little one, the top one.
Uh-huh.
When you get 2 mole of Fe, is that you get from the product side of the reaction?
Yeah, well, that's the only place I've got iron by itself, right? Yeah. All right, what in the world is going on here? Let's think through it, okay? And we'll stop after this one. I don't even know if we'll get the whole thing done, but we really need to learn how to think through some of these things. And don't get upset. This will start to become easier for you, okay? Might be a little painful at first. Your mind feels heavy. That's bad on a Friday too, isn't it? All right, we got aluminum. And it's telling me I've got some dimensions here. If I calculate that, that's going to give me the volume in centimeters cubed, right? So y'all, let's do that. I think I did it. Let me see. Y'all get upset with me though when I do this. I think I got like 10.3.
Yes.
Let's see, I've got 3. I probably need 3 to keep it at 3 significant figures though, which is 10.3. Okay. 10.3 centimeters cubed. And how did I find that? That's this right here. Okay, centimeter times centimeter times centimeter. Well, my fewest is 3.
No, I'm saying 2.3.
Because I got a decimal. And it's captive. And if it's got a decimal and I read from this way to this way, was that left to right? 1, I start counting at the first non-zero and everything after. 1, 2, 3. All right, so that gives me the volume. Let's write this reaction. A piece of aluminum foil with these dimensions is dissolved in hydrochloric acid. Those are my 2 reactants, right?
Yes.
Aluminum and hydrochloric acid. So how am I going to write this? Aluminum, that's not a Brinkelhoff, is it?
No.
So it just sits by itself. Plus,
HCl.
if you put hydro in front of it, does it have oxygen? HCl. How many grams of hydrogen gas are produced? Is that the only, this is my question, how many grams? But it's not just producing hydrogen gas. What else am I going to get? Aluminum chloride, right? What type of reaction is this? Single replacement. All right, you cannot willy-nilly write aluminum chloride. How many times have I told y'all no willy-nilly compound writing? None. It's still, aluminum is a 3+, chlorine is a 1. Those rules do not change. AlCl3. If you write anything else, it's not aluminum chloride. Okay? And then you go to balance it, and you're just messed up. Okay?
What would that look like?
All right, balance it.
Oh, God. Okay, we have to put a tree in front of that. HCl.
I'm going to write it up here too because I had a little trial and error when I did this earlier. I had put a 3 in front of that, and then I had to, mess it up, and then, yep, what else do I need? 2. So, see, I had some trial and error earlier, but there we go. I had just started with the wrong one. Now can you see, look at all these coefficients. If I had not written that correctly, I would have been way off with all my calculations, okay? All right, so now I also know the density of aluminum. Now if it gives me the density and I know the volume, can I find the mass?
Yes.
Because density is mass over volume, right? Here comes all those math skills y'all have.
So it'll be
Your unknown is the M, right?
70 equals M over 10.3. Multiply both sides by 10.3.
And I got, y'all always check behind me now, I think I got 27.8. Y'all get something around that? Feels right. That's important. Yep. That's exactly, y'all heard that? I love that. This common sense reasoning here. I said, you know, it's 27.8, is that about what y'all are getting? Does that look right? He said, yeah, well, yeah, it sounds about right. It's 2.7 times 10, right?
That's sarcastic.
No, I wasn't. I was being serious. Oh, okay. Well, I was being serious. All right. So now now I can go from, can't I go from grams of aluminum to grams of hydrogen gas now? Picket fence, gram to gram. But see, I had to find the mass of it first, and I could use the density formula to do that. So, you know, you gotta think through things, and I'm just gonna write it up here. Y'all do it. Don't look until you've got it done, and quit giving up. It is not time to go. That's okay. I can make you do extra this weekend.
Okay.
It'd be hard to go somewhere with no keys.
This McCaskill, he would go with extension cord. Now, the extension cord, extension. They hurt.
You know, Jordan's had many a wooden spoon, but he's getting too big.
And that's a good question. Ain't nothing against it at all.
I used to keep one in the glove compartment of the van so I could just reach it back there and get all of them at one time. They were stuck in that car seat. They couldn't move. I'm just mean. Y'all don't turn me in. Obviously, it didn't work. So, all right, I got this. So y'all check behind me now. And I know I wrote it up here, but oh gosh, I just recorded me talking about abusing my children with a wooden spoon. Well, see, y'all know how to do that kind of stuff. I don't know how to do that.
How to abuse
No, how to edit my little video. I know how to do. Jordan knows I know how to do. This is true. Turn myself in. All right. Now, this is just, now if you can do this is stoichiometry where we're going from this piece of the reaction to this, and we're setting up what I call a picket fence. We know that's dimensional analysis, okay? Then you can do you can do limiting and excess reactants. You can figure out how much is left over, okay? You can, if you're given enough information, you can find percent yield, okay? So that's what we need to do next week, okay? What I want to do Monday, though, we're going to do a little bit of just reviewing and doing a little bit more of this. Just a minute. And then y'all are going to do a couple of problems for me to look at Monday afternoon. And that way I'll know who needs to review what on Tuesday, and then we'll finish this up. There's not, let's see. All of this is just, shh. This is from your homework. Here it is again. Okay. We're going to figure that out. I use some different amounts here, but we're going to do that. Limiting excess, percent yield, and that's it. Okay.